Modern process and manufacturing plants are always trying to find ways to operate at higher efficiency and productivity. Better formulations, more reliable equipment, and better process control are some ways that manufacturing facilities can reach peak performance. In other RealPars videos, we learned that proper sensor calibration yields more accurate process measurements, which in turn makes good control of the process possible. When good control is realized, then the process has the best chance of running efficiently and safely. In this video series, we will learn how to achieve good control of the process by learning what a process controller is and why it's important, how a process reacts to a change in the output of the controller, how we can model the process using a first-order process with dead time equation, what proportional, integral, derivative, or PID control is, how to configure a PID controller in TIA Portal, and how to tune a PID controller to give the best control action. You may already be familiar with PID controllers, but it's important to understand the science behind the PID controller. PID is simply an equation that models the process in such a way that the result of solving the PID equation yields how the control system should adjust the process to run at a specified value. For instance, the operator in a plant may need to maintain a flow rate of water to a stripping column at 4,000 liters per hour. In this process, water is pumped through a line and a control valve, which can be adjusted to allow more flow by opening the valve a little more or to reduce the flow by closing the valve a little bit. A flow meter reports the flow by using a flow sensor and a transmitter. To control the water flow, the operator could look at the valve from the flow meter and from the HMI manually adjust the position of the feed valve to keep the flow rate at 4,000 liters per hour. While effective, this means of manual control is not very practical, since the operator would have to constantly adjust the valve position. This would be impossible in a plant with 100 different control valves. In this process example, the value of the flow that is monitored by the flow meter is called the process variable, or PV. The control valve output is called the manipulated variable, or MV. The point to which the operator would like to control the flow rate is called the set point, or SP. When operating the plant, the operator desires the process variable to be equal to the set point, so that the process is operating at the desired flow rate. However, due to many factors, such as pump performance, line pressures, or other upstream or downstream conditions, the flow rate will deviate from the set point. This deviation is called error, or E, and is equal to set point minus process variable. In order to control the flow rate at the desired set point with minimal operator intervention, I will want to create an automatic means for detecting the error and moving the position of the control valve so that the error is minimized or driven to zero. To do this, I will use a controller with the flow rate as the process variable input, calculate the required valve position to eliminate the error, and then output the calculated manipulated variable to the control valve. The simple process configuration used to accomplish this is called a control loop. Because the output of the control valve will be continuously set by the controller based upon the measured flow value, this type of loop is called a feedback control loop. The controller will need to solve an equation called a control algorithm, programmed into the controller to make the correct adjustments to the control valve based upon the flow rate detected and the value of the set point. What kind of equation should this be? To answer that question, I will need to understand how the process responds to a change in the error. The algorithm I choose will be a function of the error. When the error is small, I will make a small correction. When the error is large, a larger correction is required. But how big should these corrections be? I need to design an experiment that will tell me how the process reacts to a change in the valve position. This will give me an idea of how to configure the control equation to most effectively control my process to the given set point. To start the experiment, I will want to observe the process at steady state with a constant valve position. This will give me the first piece of information I need, the steady state value for the process variable. I will then want to make a change so that the process moves away from the current steady state, so I can observe what happens to the process. To do this, I will open the control valve an additional 10% and record the process reaction. This will generate what is called the process reaction curve. In this experiment, I have a steady state flow that has a value of 60% on the process value scale. The valve position is currently 40% output. I now increase the valve position to 50% and record the process reaction with a trend on the control system or with a data historian. After a minute, the process reaches a new steady state value. This is characteristic of what is called a self-regulating process. If a process is not self-regulating, then it cannot be modeled using these methods. Other types of processes include integrating and runaway. These will be discussed later. I will look more closely at this reaction curve. I noticed that when I made the valve output change, the process took a short time to respond to the change. This time is called dead time. It appears from the reaction curve that the dead time is approximately 4 seconds. I also noticed that the new steady state value is 67.5%. Therefore, a 10% change in valve position caused a 7.5% increase in the flow rate. The change in steady state value divided by the change in output is called the process gain. Therefore, this process has a process gain of 7.5% divided by 10%, or 0.75. Lastly, the shape of the process reaction curve looks very familiar from a mathematical standpoint. From mathematics, this curve can be approximated by a first-order exponential function. Because there is a separate dead time that precedes the exponential rise of the process reaction, we call this a first-order process with dead time, or FOPDT. In a later video, I will show you how values of the dead time, process gain, and time constant can be used to calculate important parameters that will lead to good control of the process using a PID controller. I will explain how to determine the time constant in the next video. I will show you how we can model the process using a first-order process with dead time. In this video, we learned what a feedback control loop is and how it's constructed, and how a process reacts to a change in controller output.